The 1850s were the golden age of steam expansion, and also the golden age of pretending obvious hazards didn't exist. Engineers built locomotives that could haul tremendous loads. They also built working environments so dangerous that survival often came down to pure luck. These are 20 dangers they completely ignored. Running through tunnels in the 1850s meant holding your breath and hoping for the best. Locomotives belched massive clouds of coal smoke and carbon monoxide directly into confined spaces with zero ventilation. Crews had no masks, no breathing apparatus, nothing between their lungs and the toxic exhaust billowing from their own smokestack. The physics were brutally simple. A locomotive entering a tunnel pushed its own smoke ahead like a piston, then sat in that poisonous cloud for however long the tunnel stretched. Engineers and firemen would emerge gasping, eyes streaming, sometimes unconscious at the controls. Tunnel workers clearing debris fared even worse. Maintenance crews routinely collapsed from the fumes while repairing tracks underground. The Baltimore and Ohio's tunnels became particularly notorious. Crews called certain runs suicide shifts because the smoke concentration could render a man unconscious in minutes. Some railroads experimented with timing train passages to allow smoke clearance between runs. Most didn't bother. The solution seemed obvious: improve ventilation or modify exhaust routing, but that cost money. So engineers kept running blind into smoke-filled darkness, gambling they'd reach the other side before the carbon monoxide won. Locomotives in the 1850s routinely barreled through pitch darkness with lighting that wouldn't illuminate a decent-sized closet. Early headlights were little more than oil lanterns mounted on the smokebox, casting perhaps 50 feet of dim yellow glow. At 30 miles per hour, that gave engineers roughly 1 second of warning before hitting whatever lurked on the tracks ahead. Stopping distances far exceeded visibility distances. Engineers couldn't see obstacles until they were already committed to colliding with them. Livestock wandered onto tracks constantly since open-range grazing was common. Fallen trees, rock slides, broken rails, all invisible until the moment of impact. Some railroads issued written instructions that essentially told engineers to proceed cautiously and pray. The Pennsylvania Railroad's early rulebook acknowledged that night running was inherently dangerous, but offered no practical solutions beyond reduced speeds that shareholders wouldn't accept. Improved kerosene headlights appeared later in the decade, but adoption was slow and inconsistent. Many railroads considered adequate lighting an unnecessary expense. The logic was that accidents were cheaper than equipment upgrades, at least until the lawsuits started accumulating. By the late 1850s, the telegraph revolutionized railroad dispatching. It also created entirely new ways to die. Dispatchers transmitted orders in Morse code to station operators who copied them by hand, then passed those handwritten orders to train crews. Every step introduced potential for fatal error. A single misread dot or dash could transform a meat order into a collision course. Station operators worked long shifts in noisy environments, copying messages under pressure while multiple trains waited. Penmanship varied wildly. An engineer squinting at scrawled instructions in poor lighting might misread a crucial detail: the wrong track number, an incorrect time, a misspelled station name. The system had no verification protocols. Once an order left the dispatcher's key, it traveled through multiple human hands with no confirmation that the final version matched the original intent. A famous collision near Burlington in 1855 killed 21 people when conflicting orders sent 2 trains toward each other on the same track. Investigators found the telegraph message had been transcribed correctly, but one operator interpreted the timing differently than intended. The technology that promised safety had simply relocated the danger. Engineers and firemen in the 1850s worked until they couldn't physically continue, then worked some more. 18-hour shifts were common. 24-hour marathons weren't unusual during busy periods. Railroads treated crew fatigue as a personal failing rather than a systemic hazard. The consequences were predictable. Exhausted engineers fell asleep at the throttle, missing signals and station stops. Firemen nodded off while monitoring water levels, allowing boilers to run dangerously low. Brakemen stumbling across car roofs in the dark made fatal missteps because their reflexes had abandoned them hours earlier. Management's attitude was brutally pragmatic. Training replacement crews cost money. Running existing crews into the ground cost nothing on paper. When accidents occurred, companies blamed individual negligence rather than examining scheduling practices. Some engineers reported working 72 hours straight during peak traffic, sustained by coffee and desperation. Medical understanding of fatigue's effects on judgment barely existed. The concept that sleep deprivation could impair performance as severely as intoxication wouldn't gain acceptance for another century. Meanwhile, engineers operated complex machinery while barely conscious. Every railroad in the 1850s invented its own rules, its own signals, and its own procedures. An engineer who worked perfectly safely on one line became a liability the moment he crossed onto another railroad's tracks. Hand signals meant different things to different companies. Whistle codes varied wildly. What indicated stop on the Pennsylvania might mean proceed with caution on the Baltimore and Ohio. This chaos extended to basic operations. Some railroads gave eastbound trains priority. Others favored westbound. Some used red flags for danger, others used, or white. Train crews transferring between railroads faced a terrifying learning curve where mistakes could be fatal. Even within single companies, rules changed between divisions. A conductor who knew the Northern Division's procedures might find himself completely disoriented on the Southern Division. The resulting confusion caused countless collisions and derailments. Experienced railroaders carried mental libraries of contradictory rules, trying to remember which procedures applied to which stretch of track. Industry standardization wouldn't arrive until decades later, driven by accumulated disasters that finally convinced competing railroads that dead passengers were bad for everyone's business. Railroad expansion in the 1850s outpaced engineering wisdom. When tracks needed to cross valleys, rivers, or ravines, builders threw up wooden trestle bridges with terrifying speed. These structures used timber framing that could be erected in weeks rather than the months required for stone or iron construction. The cost savings were substantial. So were the risks. Wooden trestles rotted from within, their decay invisible until catastrophic failure. Heavy rains swelled rivers that undermined foundations. Fire from locomotive sparks could destroy an entire bridge in minutes. Maintenance inspection was haphazard at best. Many railroads considered bridges sound until they actually collapsed. A trestle near Norwalk, Connecticut failed in 1853 when the drawbridge operator forgot to close it, sending a train into the river and killing 46 people. But structural collapses were equally common. Timber that looked solid might be hollowed by rot or weakened by insect damage. Engineers crossing trestles learned to listen for unusual sounds, creaking or cracking that might signal imminent collapse. They also learned to accelerate, reasoning that getting across quickly reduced exposure time to whatever might happen beneath the wheels. In the 1850s, trains followed each other, with nothing but faith and scheduling between them. The block signal system, which divided tracks into protected sections, existed in theory, but rarely in practice. Most American railroads relied entirely on timetables, assuming trains would maintain their schedules with clockwork precision. Reality intervened constantly. A locomotive that broke down mid-run became invisible to following trains. There was no way to communicate a problem backward along the line. Engineers approaching a stalled train had no warning until visual contact, which at operating speeds meant seconds before impact. The instructions given to engineers were almost comically inadequate. Proceed at such speed that you can stop within your range of vision. On curves, in tunnels, in fog, in darkness. This was impossible. Rear-end collisions became so common, they earned their own railroad terminology and their own resigned acceptance. Some railroads employed flagmen who would walk backward along the track after a stop, placing warning signals. But this took time, and following trains didn't always allow enough interval. The fundamental problem remained. There was no mechanical system preventing trains from occupying the same track space simultaneously. Opening a locomotive firebox door in the 1850s was an act of calculated risk. Firemen fed coal into roaring furnaces dozens of times per hour, and each opening created opportunity for disaster. A sudden change in draft, caused by tunnels, wind shifts, or throttle adjustments, could reverse the airflow and blast superheated gas directly into the fireman's face. These blowbacks happened without warning. One moment, a fireman would be reaching toward the firebox with his shovel. The next, he'd be engulfed in flames and steam, hot enough to cook flesh instantly. Survivors described the sensation as being hit by an invisible wall of fire. The cab offered no protection. Early locomotives had minimal shielding between crew and machinery. Firemen worked inches from the firebox opening, fully exposed to whatever came out. Burns were an occupational expectation rather than an exception. Experienced firemen developed techniques to minimize exposure, angling their bodies, using long-handled shovels, timing their actions to the locomotive's rhythm. None of this was foolproof. The fundamental design placed human beings directly in the path of potential thermal eruptions, and nobody seriously considered redesigning it. Locomotive cabs in the 1850s offered crews about as much protection as a covered wagon. Many early designs had no enclosed cab at all, just a small roof over the engineer and fireman's positions. Side walls, when they existed, were often partial, leaving crews exposed to wind, rain, snow, and flying debris. Operating in winter meant enduring temperatures that could freeze exposed skin in minutes. Engineers and firemen bundled in layers of wool, their hands barely functional inside heavy gloves that made operating controls difficult. Frostbite was routine. Hypothermia was a genuine risk on long runs through mountain passes. Summer brought different torments. Crews roasted between the firebox heat behind them and direct sun above. Cinders and hot ash from the smokestack rained down constantly. Burns from flying embers were so common that railroad crews developed distinctive scarring patterns. The cab's exposure also meant vulnerability to trackside hazards. Tree branches, low bridges, and debris struck crews with regularity. Engineers learned to duck instinctively at certain locations, knowledge passed down through painful experience. Full cab enclosures would come eventually, but the human crew remained the least protected component. Passenger cars of the 1850s were wooden boxes heated by cast iron stoves burning coal or wood. When these cars derailed or collided, the stoves tumbled from their mountings, scattering burning coals across splintered wooden wreckage. Passengers who survived the initial impact often burned to death in the fire that followed. The design flaw was obvious to everyone and addressed by no one. Wooden cars were cheap to build. Metal alternatives existed but cost more. Railroads calculated that the occasional fire death was an acceptable price for lower construction expenses. Insurance would cover lawsuits. Passengers sat in elaborately decorated fire traps, their ornate woodwork soaked in varnish that accelerated flames beautifully. Heating alternatives were proposed, but rarely implemented. The Angola horror of 1867 would eventually force change, when 49 people burned alive after a derailment sent stove coals throughout the wreckage. But throughout the 1850s, the danger remained theoretical enough for railroads to ignore. Engineers knew their passengers rode in kindling boxes. They also knew that expressing such concerns publicly would cost them their jobs. The business of railroading prioritized economy over safety. Iron rails in the 1850s had a fatal flaw that winter exposed with brutal regularity. The metal became brittle in cold weather, snapping under the weight of passing locomotives with no warning whatsoever. An engineer would be running along perfectly sound track when suddenly his wheels would drop into a gap where moments earlier solid rail had existed. Temperature swings made the problem considerably worse. Rails contracted in freezing weather, opening dangerous gaps at joints. The same rails that seemed perfectly secure on a mild afternoon might fracture catastrophically on a frigid morning. Engineers learned to dread the sharp crack of breaking rail, a sound that meant instant disaster. There was no time to react, no chance to stop. By the time you heard the snap, you were already derailing. The solution was steel rail, which resisted cold weather brittleness far better than iron. But steel cost significantly more to manufacture, and most railroads refused to invest until the accident toll became impossible to ignore. Throughout the 1850s, trains continued running on iron rails that might shatter at any moment, their engineers gambling that this particular cold morning wouldn't be the one where the metal gave way. Most American railroads in the 1850s operated on single track, with trains running both directions on the same rails. The system depended entirely on scheduling. Eastbound and westbound trains were supposed to meet at designated passing sidings, where one would wait while the other proceeded. When the system worked, it worked elegantly. When it failed, trains met head-on at combined speeds approaching 60 miles per hour. The failures happened constantly. A delayed train might miss its scheduled meet. A conductor might misread his orders. A station operator might forget to display the proper signals. Engineers learned to watch for telltale smoke ahead, the only warning that another train occupied their track. Even then, stopping was usually impossible. The physics of momentum guaranteed that by the time you saw the other locomotive, you were already committed to collision. Some engineers survived by jumping clear at the last possible moment. Many didn't have time. Head-on collisions became so common that railroad men developed a grim fatalism about the odds. Brakemen in the 1850s earned their wages walking across the roofs of moving freight cars. Before air brakes existed, stopping a train required manually turning brake wheels on individual cars. When the engineer whistled for brakes, brakemen scrambled up ladders and ran across car roofs, spinning wheels as they went. The job was dangerous in perfect conditions, and suicidal in anything else. Rain made rooftops slick as ice. Snow obscured the gaps between cars. Darkness turned the journey into pure guesswork. Wind could knock a man off balance at the worst possible moment. Tunnels and low bridges added another dimension of terror. A brakeman focused on his brake wheel might not notice the overhead clearance approaching until it was too late. Railroad veterans spoke of colleagues who simply vanished during tunnel passages, swept off by structures they never saw coming. The mortality rate among brakemen was absolutely staggering. Some estimates suggest that 1 in 4 brakemen would die or be seriously maimed during their railroad career. The job attracted young men who needed money badly enough to accept those terrible odds, and it killed them with mechanical efficiency. Coupling railroad cars in the 1850s required a man to stand between two moving vehicles and guide a heavy iron link into a socket, then drop a pin to secure it. The timing had to be perfect. The cars approached each other at walking speed, their massive weight building unstoppable momentum. The coupler had seconds to position the link, drop the pin, and get clear before the gap closed. Get it wrong, and thousands of pounds of rolling iron would crush whatever stood between the couplers. The injuries were characteristic and horrific. Crushed hands, severed fingers, mangled arms. Death from being caught between cars that didn't stop when they should have. Experienced couplers developed techniques to minimize risk, standing sideways, using their bodies as wedges, timing their movements precisely to each car's momentum. None of this made the job safe. It just made survival slightly more probable. Railroads knew the link and pin system was killing their workers regularly. Safer automatic couplers existed by the 1870s. But conversion cost money, and brakemen were cheap and replaceable. Building railroads in the 1850s meant choosing a track gauge, and everyone chose differently. The Erie Railroad used 6 feet between rails. The Pennsylvania used 4 feet 8.5 inches. Southern railroads often used 5 feet. Some lines used gauges that existed nowhere else. The result was chaos at every junction where different railroads met. Freight couldn't simply roll from one line to another. Everything had to be unloaded, transferred to different cars, and reloaded. Passengers walked between trains. Goods sat in warehouses waiting for transshipment. Through traffic was essentially impossible. The inefficiency was staggering, but the incompatibility also created safety hazards. When tracks of different gauges converged, the resulting track geometry confused even experienced engineers. The safety valve was supposed to be the last line of defense against boiler explosion. When pressure exceeded safe limits, the valve would open automatically, releasing steam and preventing catastrophic disaster. The design was elegant and simple. The implementation was sabotaged constantly by the very crews it was meant to protect. Engineers and firemen hated safety valves intensely. Every pound of steam escaping through the valve was pressure that couldn't drive the pistons. A locomotive with a properly functioning safety valve was a locomotive that couldn't achieve maximum power. So crews tampered with them relentlessly. They weighted the valves with extra metal. They tightened springs beyond specification. They jammed the mechanisms so valves couldn't open at all. Management often encouraged this behavior indirectly, rewarding engineers who made faster runs without asking how they achieved that extra speed. The first recorded locomotive boiler explosion in America happened in 1831, when a fireman, annoyed by the hissing of the safety valve, sat on it to keep it quiet. The boiler exploded moments later. Throughout the 1850s, valve tampering remained common practice. The crown sheet was the metal plate forming the top of a locomotive's firebox, the barrier between water in the boiler and fire below. As long as water covered the crown sheet, it stayed cool enough to maintain structural integrity. Let the water level drop, and the exposed metal would overheat rapidly, losing strength until it couldn't contain the immense pressure above. The failure was catastrophic and unsurvivable. Superheated steam would blast downward through the ruptured crown sheet into the firebox, then explode outward through the cab. Crews caught in a crown sheet failure were essentially cooked alive by steam and scalding water. The violence of the release often hurled bodies and locomotive components hundreds of feet from the track. Preventing crown sheet failures required constant attention to water levels. But water gauges were crude, often inaccurate, and difficult to read in the dim, vibrating cab. Climbing grades would shift water toward the rear of the boiler, exposing the front of the crown sheet even when gauges showed adequate levels. Exhausted firemen might misjudge their readings. Distracted engineers might not notice the danger until it was too late. Before telegraph dispatching became widespread, American railroads operated on nothing but printed timetables and faith. Each train had scheduled times for departing stations, arriving at junctions, and meeting opposing traffic at designated sidings. The system assumed every train would run exactly on schedule. Every crew would follow their orders precisely, and nothing unexpected would ever happen. Reality was considerably messier than any timetable could accommodate. Locomotives broke down, weather delayed departures, crews misread their schedules. A train running late might find itself on a collision course with opposing traffic that expected clear track. There was no way to communicate changes once a train left a station. An engineer running behind schedule had to guess whether opposing trains were waiting at sidings or barreling toward him on the main line. Some railroads gave superior trains absolute priority, forcing inferior trains to wait indefinitely at sidings until the superior train passed. This created cascading delays that rippled through entire systems. One miscalculation could send 2 trains into the same stretch of single track with no warning. Nothing in 1850s railroading killed with such sudden violence as a boiler explosion. One moment, a locomotive would be running normally. The next, the boiler would rupture with the force of a bomb, hurling iron shrapnel in every direction, launching the locomotive's shell like a cannon projectile, and scalding everything within reach with superheated steam. The physics were terrifying. A locomotive boiler contained thousands of gallons of water under immense pressure. When containment failed, that water flashed instantly to steam, expanding to 1,700 times its liquid volume. The energy release was equivalent to several hundred pounds of dynamite. Boiler explosions threw locomotive components half a mile. They killed crews, passengers, and bystanders who happened to be standing nearby. They left craters in the roadbed. The causes were multiple: corroded metal that had weakened invisibly.
Engineers and designers constantly pushed boundaries.
Steam would spin a turbine, then drive an electrical generator, and that would power traction motors.
Greater efficiency and increased power. But not every experiment succeeded. That railway authorities decided they could never safely or economically operate again.
Smooth, quiet, efficient. The reality was a mechanical nightmare.
Some locomotives had flaws so fundamental, trying new concepts and technologies in the pursuit of better performance.
Bearings failed. Generators overheated. The condensing system, essential for turbine efficiency,
but more commonly known as Fury. This machine was designed to operate at extremely high boiler pressure. The locomotive was fitted with a Hypersure Schmidt boiler operating at 900 pounds per square inch.
Test runs revealed a machine that consumed coal at terrifying rates,
nearly double the pressure of conventional locomotives at the time. This required special materials and construction techniques.
Within months, the North British Locomotive Company quietly rebuilt the entire locomotive with conventional direct drive turbines, hoping to salvage something from the disaster.
The Fury, London Midland and Scottish Railway's Hypersure experiment in 1929. The London Midland and Scottish Railway embarked on an ambitious project to develop a Hypersure steam locomotive. These are the stories of 7 such machines. Number 7, that would set new standards for efficiency. The result was a locomotive initially numbered 6,399. The engineers behind Fury believed that by dramatically increasing boiler pressure
while producing barely adequate power, mechanics spent more time repairing it than running it. The rebuilt machine limped through a handful of tests before being abandoned entirely due to persistent mechanical failures that made it utterly useless for regular service. In 1933, Italian state railways decided to transform a perfectly good Class 685 locomotive
and specialized knowledge that most railway workshops simply didn't possess. Then, during a test run in 1930, the boiler tubes and fittings were operating at the very limits of available materials technology. Testing began in 1930, and initial results seemed encouraging, making Fury one of the most technically advanced locomotives of its era. They could extract significantly more work from each pound of steam generated.
Proved hopelessly inadequate in the confined spaces of a locomotive. Engineers removed the reliable piston engine and installed a steam turbine in its place, leaving everything else completely unchanged. The locomotive still looked like a standard 2/6/2 wheel arrangement, but now it had turbine gearing where pistons once lived. The results were catastrophic. Performance plummeted to levels well below the original piston-driven locomotive. The turbine simply could not deliver power efficiently across the speed ranges that railway operation demanded. Maintaining speed on grades proved nearly impossible. The boiler, designed for a reciprocating engine's intermittent steam demand, within months, the turbine mechanism literally broke apart during testing. Metal fragments scattered through the machinery as stressed components gave way. They simply refitted the locomotive with a conventional piston engine in 1936 and pretended the whole turbine episode never happened. Italian engineers did not bother rebuilding the experiment. The failed conversion stood as proof that bolting new technology onto old designs rarely ends well. Ross Winans built his first camel locomotives for the Baltimore and Ohio Railroad starting in 1848, and from the beginning, crews knew something was terribly wrong. Winans wanted maximum weight over the driving wheels for better traction,
and served as a sobering reminder that technological ambition must be balanced with safety considerations. Number 6. The locomotive was later rebuilt with a conventional boiler and renamed. This incident shocked the railway industry and raised serious questions about the viability of ultra-high-pressure steam technology. were unacceptable. The materials and engineering knowledge of the time were simply insufficient to safely operate boilers at these pressures. Fury was withdrawn from service immediately.
The fireman worked alone on a platform at the rear, completely exposed to weather and separated from the engineer by an entire roaring boiler.
The result was a machine that looked unlike any steam locomotive before it. The crew member in the fireman's position suffered fatal injuries from the escaping steam. Following a thorough investigation, railway authorities concluded that the risks associated with such extreme pressures developed one of the most unconventional steam locomotives ever built in Britain. The leader class was designed to combine the efficiency of steam power.
Despite these dangers, Winans built hundreds of camels, prioritizing fuel savings over human safety. The Pennsylvania Railroad's engineering department in the 1930s sketched designs for what would have been the most ambitious articulated locomotive ever conceived.
Perhaps most critically, the leader's performance failed to justify its complexity and cost. By 1950, with British Railways already committed to desalination, continuing with the leader project made little sense. Only one leader was completed, and it operated for barely a year before being permanently withdrawn in 1950. Tragedy occurred. A boiler tube failed catastrophically, releasing superheated steam at 900 pounds per square inch.
Railroad workers called these locomotives dangerous long before safety regulators existed. Engineers perched directly above the whirling side rods and main rods, with nothing but thin cab walls between them and disaster.
This design offered numerous advantages, including better working conditions for crews, reduced turnaround times, and improved visibility. Construction of the first leader began in 1948, and it was completed in 1949. However, problems emerged as soon as testing began.
The locomotive would have exhausted its steam reserves within seconds of starting, leaving a £250,000 machine stranded on the main line. Pennsylvania Railroad engineers quietly shelved the proposal, recognizing that ambition had outpaced physics.
The leader featured a completely enclosed design with driving cabs at both ends, eliminating the need to turn the locomotive at the end of each journey. The boiler and machinery were housed in a central section, with the crew protected in comfortable, fully enclosed cabs. On paper,
3 of these 106-foot monsters were built by Baldwin Westinghouse to prove that steam could compete with diesel on premier passenger runs.
As speed increased, diesel fuel was injected, and the engine transitioned to diesel operation, with steam providing assistance.
Water from the condensing system followed the dust, turning coal residue into an abrasive slurry that destroyed electrical components. The locomotives could not complete a single journey from Washington to Cincinnati without suffering some kind of failure. After spending millions on development, the C&O operated their M1s for barely a year before giving up.
Number 5. The Kitson-Still locomotive. In the 1920s, engineers were exploring ways to combine the best features of steam and internal combustion engines. The complex chain-driven mechanism that transmitted power to the wheels proved troublesome, requiring frequent adjustment and repair. Reliability was poor, with the locomotive spending far more time under repair than in service.
The proposed V1 class would have featured 4 complete engine units, essentially quadrupling the triplex concept that had already proven problematic on the Erie and Virginian railroads. Internal documents show engineers planning for over £200,000 of tractive effort. The reality proved humiliating. This massive machine could barely sustain 5 miles per hour. The boiler, despite being larger than anything previously attempted, simply could not generate enough steam for 6 enormous cylinders operating simultaneously. Crews watched pressure gauges drop towards zero within moments of opening the throttle. The rear engine set mounted under the tender lost traction as coal and water were consumed,
creating confusion and errors. Performance testing revealed that the Kitson-Still failed to deliver on its promises. The transition between steam and diesel operation was rough and inefficient. The engine consumed more fuel than a conventional diesel locomotive while producing comparable power, spending much of that time under repair or modification. Engineers attempted various fixes.
After less than 5 years of frustrating service, the Virginian returned the locomotive to Baldwin, who cut it apart and rebuilt it as 2 separate, conventional locomotives. Baldwin built the first triplex for the Erie Railroad in 1914, naming it the Matt H. Shea, after a beloved company engineer. The reality proved that some problems cannot be solved by simply adding more cylinders. The Matt H. Shea generated 160,000 pounds of tractive effort, more than any steam locomotive before or since. This massive force immediately created new problems. Couplers snapped, car frames twisted, drawbars pulled out of freight cars like corks from bottles.
The locomotive, delivered in 1925, was a massive articulated machine with separate engine units at each end and the boiler suspended between them. The railway industry concluded that specialized locomotives, whether pure steam or pure diesel, were more practical than attempting to combine both technologies in a single machine. Number 4. The Biograt oil burning experiment for London transport in the 1920s. By 1931, it was clear that the kits and still concept was not viable for railway service. The locomotive was withdrawn and eventually scrapped in 1935. The tremendous tractive effort it could develop was rarely needed on the Metropolitan Railway's routes. The articulated design, while allowing it to navigate curves, made it longer than conventional locomotives.
By 1929, all had been scrapped, having proven that maximum power means nothing when your boiler runs dry. But the locomotive's problems proved impossible to hide. Nigel Gresley designed it with a water tube boiler operating at 450 pounds per square inch, more than double the pressure of conventional locomotives.
But the original oil-burning configuration never ran again. This experience demonstrated that technological solutions must be matched carefully to operational requirements, and that complexity doesn't always equal improvement.
Marine engineers had proven high-pressure water tube boilers worked brilliantly in ships, but railway operation proved far less forgiving. Steaming proved so poor that the locomotive could not match the performance of standard Gresley Pacifics despite its advanced technology. The compound expansion system required constant adjustment.
The gas turbine engine could produce far more horsepower than contemporary diesel locomotives. The burners were temperamental and difficult to adjust properly. When not perfectly tuned, they produced excessive smoke and soot, defeating the entire purpose of using oil fuel. London's Metropolitan Railway needed powerful locomotives to haul heavy commuter trains through the increasingly congested underground sections. The railway ordered a specialized Biograt articulated locomotive. Fuel consumption was the most obvious problem. The turbines burned bunker sea fuel oil, a thick, heavy residue left over from petroleum refining. While this fuel was cheap, the turbines consumed it at extraordinary rates.
After 7 frustrating years, the LNER admitted defeat and rebuilt the entire locomotive with a conventional boiler in 1936.
The turbines were sensitive to fuel quality, and contamination could cause rapid deterioration of turbine blades.
Turbines require high rotational speeds to operate efficiently, and gearing that worked beautifully at highway velocities proved catastrophic at yard speeds.
Union Pacific eventually developed improved turbine designs that addressed some of these issues, but the earliest experimental units were deemed beyond economical repair. But they also demonstrated the challenges of introducing radically new technology to railway operations.
The locomotive was scrapped in 1952, having logged just 103,000 miles before proving turbines belong in power plants, not on rails. Above 40 miles per hour, the turbine consumed less fuel than conventional locomotives while delivering smooth, silent power.
These early turbines were designed to provide immense power for hauling freight across Union Pacific's western routes.
Baldwin and Westinghouse delivered this 686 direct drive turbine locomotive in 1944, erasing Gresley's ambitious experiment and proving that shipboard success does not translate to railway tracks. The Pennsylvania Railroad S2 was supposed to prove that steam could outperform diesel at its own game. This steam turbine electric stretched 161 feet from coupler to coupler, making it the longest steam locomotive ever constructed. The boiler operated at 600 pounds per square inch, nearly double conventional pressure. The design promised to preserve coal hauling jobs in Norfolk and Western's Appalachian Territory by proving steam could match diesel efficiency. Coal dust infiltrated the electrical equipment constantly, destroying traction motors and generators. The complex controls confused even experienced engineers, leading to mistakes. Performance ran 15% below the conventional Class A locomotives it was supposed to replace. Norfolk and Western scrapped it in 1958, the last desperate gasp of steam dying 4 years after birth.
But some of their more experimental units proved deeply problematic and were withdrawn after brief service. However, several design issues made some Sentinel railcars unpopular and ultimately unworkable. Articulated designs intended to increase capacity were structurally weak and suffered from cracking and frame failures. Steam leaks, engine troubles, and boiler issues kept them out of service frequently.
The locomotive's extreme length meant it could not use any turntable on the Norfolk and Western system. The Pennsylvania Railroad's T1 duplex looked magnificent and ran like a nightmare. 52 of these streamlined 4444 locomotives were built between 1942 and 1946, designed by Raymond Loewy to be the fastest passenger power in America. They achieved that goal, reportedly touching 140 miles per hour on test runs. The poppet valves, chosen for quick steam admission, made problems worse by delivering power in sudden bursts.
The failures of these experimental steam railcars helped accelerate the transition to diesel railcars on British branch lines. In the 1950s, South African railways experimented with condenser locomotives.
Crews accustomed to conventional Pacifics found themselves wrestling machines that responded to throttle inputs in unexpected ways.
The vertical boiler design was compact and efficient for its size, and the high-speed engine could propel the railcar at respectable speeds. These railcars combined a small vertical boiler, a high-speed steam engine, and passenger accommodation in a single vehicle.
The locomotive's fate proved grimly appropriate. Built by Baldwin Westinghouse in 1954, by 1949, severe turbine damage ended the experiment. The London, Midland and Scottish Railway locomotive number 6399, Fury, represented Britain's most ambitious attempt at high-pressure steam, and it ended in death. Fury operated at pressures ranging from 900 to 1,800 pounds per square inch in its ultra-high pressure circuit. The theory promised dramatic fuel savings through thermodynamic efficiency. During a test run from Glasgow to Carstairs, one of the ultra-high pressure tubes burst catastrophically. Scalding steam and boiling water erupted through the cab, ejecting burning coals from the firebox. Lewis Schofield, an engineer from the superheater company who was riding on the footplate to monitor performance, suffered horrific burns. Investigators at Sheffield University examined the burst tube but never determined a definitive cause. In 1935, the railroad admitted defeat and rebuilt the locomotive with a conventional boiler. It was so secret that only one official photograph exists, and its problems explain why the railway wanted it forgotten. This bizarre 262 wheel arrangement featured 8 uniflow cylinders arranged in 2 groups between the driving axles, all controlled by rotary sleeve valves. The bronze sleeves operating inside cast iron steam chests could not handle thermal expansion. As the engine heated up, different metals expanded at different rates, causing the sleeves to seize solid, stranding the locomotive on the main line for 7 hours, while crews struggled to free the mechanism. The constant leakage past the 192 piston rings required for the sleeve valve system wasted steam continuously.
Fans drove air through these condensers, cooling the exhaust steam and converting it back to water. In theory, this should have allowed almost indefinite operation without taking on water, where the challenging operating environment of the semi-arid Karoo region inspired unusual locomotive designs.
This made the T1 extraordinarily prone to wheel slip, violent wheel slip that occurred without warning at any speed. Engineers reported front drivers spinning wildly, while rear drivers gripped normally, sending shudders through the locomotive.
Operating departments found them unreliable and difficult to maintain with standard railway facilities. The specialized knowledge required to service these unusual machines was often not available at smaller depots. The ride quality was often poor, with vibration from the engine and rough suspension making passenger travel uncomfortable. The vertical boiler, while space efficient, was difficult to maintain and prone to steaming problems. Water capacity was limited, requiring frequent stops for refilling. Some experimental variants incorporated unusual features that proved impractical.
But the T1s concealed a fatal flaw that made them nearly uncontrollable. The divided drive arrangement placed two sets of driving wheels on a rigid frame, each powered by its own cylinders. Instead, it demonstrated everything wrong with late-era steam technology. The water tube boiler required specialized maintenance that most crews could not perform. Wheel slip damaged valve gear, which caused more slip. By 1948, the Pennsylvania Railroad had begun replacing their revolutionary T1s with diesel locomotives. Every single locomotive was scrapped. None were preserved. The entire fleet was erased from existence. Norfolk and Western's John Henry earned its nickname from the legendary steel driving man who raced against a machine and won, only to die from the effort. Low water exposing the crown sheet, disabled safety valves that couldn't release excess pressure, poor maintenance that allowed scale buildup. Throughout the 1850s, boiler explosions occurred with horrifying regularity. Engineers knew the risk every time they climbed into the cab. And that's all, folks. 20 dangers that steam engineers faced daily, and 20 hazards that the industry chose to ignore until the body count became impossible to deny. Don't forget to subscribe. Here's another video I've specially selected for you. See you next time.